and welcome to our presentations. We will be discussing our research, scaling, and timing adversarial training with synthetic data. Okay, let's begin with some background on our topic, adversarial attack. The adversarial attack involves adding a small perturbations to the original input data and generating an adversarial sample that causes the model to make incorrect predictions, and these perturbations are not easily visible to the human eyes. However, they can mislead the model into making wrong decisions. That's the problem. For example, FGSM is a basic simple step attack. As showing this image, a picture originally classified as a pandas, maybe is misclassified as a medal after small perturbations is added. It is just one type of the attack. More advanced methods like PGD involve multi-step iteration attack, creating even stronger attacks. So our research focuses on improving the model ability to resist such misleading input, enhancing its robustness. So moving on to related work, as we mentioned earlier, the adversarial training, the AT, is a well-established and effective strategy, effective strategy for defending against such an adversarial attack. However, with the rapid advertisement in generative models, such as the diffusion models, as shown in this diagram, the generated data the idea is to combine the real data and synthetic data to generate the adversarial samples, and this adversarial training process involves the iterations, these products multiple times, with the model continually adjusting to become more resistant to the adversarial attack, and both the real and synthetic data can generated the adversarial samples, so serving as the foundation for the adversarial training. And the limitation is most of the existing synthetic data based on the synthetic data-based adversarial training have been primarily focused on maybe small-scale data set, such as CIFAR-10 or CIFAR-100. Unfortunately, there is a limit work done on applying this method to maybe large-scale dataset like ImageNet. So this gap presents a challenge that we aim to address in our research. And we demonstrate that what's our contributions. We demonstrate 50 million synthetic sample enhance the adversarial robustness on ImageNet, and without relying on any other external data, and providing the power of diffusion-based synthetic data. That is the initial improvement. And by scaling both the model and synthetic data, we also achieve a better performance on large-scale models with around 71% robustness accuracy on ImageNet 1K under the auto attack. And we also, during this process, we also find and tackle up new phenomena or a new problem, stabilizing the large-scale training. That's the main point. And let's talk about our methodology. Simply put, in our preliminary explorations, we aim to extend the existing work by utilizing the synthetic data, optimize the architectures, and improve the training protocol, etc., to enhance the adversarial performance of mainstream models. And we also designed a two-phase training process, got an initial improve. And in our further explorations, our objective was to scale up the model architecture to over maybe about 500 million parameters in order to exploit the potentials of large-scale training for more practical applications. However, during this process, we encounter a new phenomenon, as we mentioned earlier, which we call the loss oscillations. This occurred when the training loss suddenly dropped, causing the training process to fail for larger model. This was a crucial challenge that we need to adjust. So the main work is about measurement strategy and optimize training approach. As you can see, the EQ rate and the A side or the stable PGD. And let's take a close look at the method. The EQ rate is used to gauge whether two adversarial perturbations are nearly identical. In other words, it's quantifying the oscillation during the PGD optimization, providing insight into how much the perturbations are repeating or cycling, and the EQ rate measures the equality between two perturbations, where the value closer to 1 indicates high similarity, while the value close to 0 indicates more diverse perturbations, put on simply term, and we try to quantify the oscillation, And then look at the A side or the stable PGD. The main goals of this method is to optimize the PGD's the signed update, which is a key component of adversarial training. Specifically, our approach scales the signed update for weak gradients while keeping strong gradients unchanged. And this helps to ensure the updates made to the models are more controlled and effective. In addition, we use the magnitude information to suppress the overshooting, which is common issues in the adversarial training. And this is how the model avoids making maybe overly large step that can destabilize the training process. Hence, let's now look at the experimental result. As we mentioned, the preliminary exploration that is got initial improvement. This comparison highlights the strengths of our method in improving robustness and maybe the clean accuracy, while maintaining competitive standard accuracy. We got large improvement in the mainstream models. Absolutely, we align with the existing benchmark standard and move on to further explorations based on our method. As seen in this picture, the training loss curves, we encountered the loss oscillations in the original method. You can see the red line and where the loss fluctuates significantly. And the other method also making the training unstable. And our method successfully stabilized the training process, as you can see, demonstrate the effectiveness of our method in addressing the issues of loss oscillation during the large-scale adversarial training. And in evaluating the large-scale model, as you can see, our approach with 50 million synthetic data achieving the robustness accuracy of around 71% and demonstrate the effectiveness of our approach in addressing the issues of the loss oscillations and effectiveness of our method. Okay, due to the time constraints, we have provided a brief overview. If you are interested, feel free to read our full paper. Thank you for your listening.